I don't know what time it technically is in Nova Scotia because they have a slightly different time zone, I believe, but it's 1 p.m. here in the Eastern time zone. So we're going to go ahead and start our webinar, which means we're going to start the recording of this presentation. This one, Dave Giles is going to lead us on this as our EV expert. He mentioned it is a great time to talk about heat exchangers now that the weather's getting lousy, and how that works in electric vehicles. It's a little bit different than standard ICE vehicles, and Dave's kind of our expert leading the way on this. He's going to talk about octovalves and supermanifolds, and I wanted everybody out to know that if you stay through the end of this presentation, we are going to be sending certificates of participation to everybody. We're going to capture everybody's emails, and you'll get a certificate from us that you attended this for your PE, should you need it. And then, as usual, if you've attended any of our discussions, we do have the chat open. Or no, we don't have chat open. We will use the Q&A as usual. So if you've got a question, go ahead and put it in the Q&A, which is right next to the chat feature. Put your question there, and then once Dave's done, we'll start firing some questions to him. Definitely don't hesitate to ask questions. And with that, I'm going to hand this over to Dave Giles, our electric vehicle expert.
Thanks, Jimmy. Anyway, so I'll welcome everyone today to today's episode of Octovalve and Supermanifold. It's actually one of the same, so I'm going to go through it. I do have a live presentation as well, too, so I'm going to move right through this. There's lots to cover. It's a very unique system, very advanced system in what Tesla has done. So
Dave, you're muted.
Did it just get muted, or did...
Yeah, you got muted, so just go ahead and start from there.
Okay, must have been talking too loud. So heat pumps started in Teslas in 2020 Model Y year. The Model 3 didn't follow till about 2021, and now they all have adopted the exact same heat pump system, which is really unique because the heat pump you find in a Model Y is identical heat pump that you would find in a Model S Plaid or a Model X, and also in the Model 3. There's a few little changes they made, which I'll talk about today's episode. As I move through this presentation, we're going to leave a little bit of time at the end for questions. I hope I'm going to move fairly quickly, but I'm going to keep it fairly high level. I do want to plan on doing a little bit more in-depth breakdown training with the Tesla's heat pump system. It's very unique, very cool. Lots of really cool stuff you're going to see in this presentation. Basically, how do you know if the vehicle has a heat pump system? In the menus on the screen of the vehicle, when you go into a Tesla, the main information display, there's a little car icon, usually in the lower left corner, in the Model 3 and Model Y specifically. You click on that, or you push that, you'll come up with a big menu. There'll be software. And under the software, you'll see additional information. And that additional information will tell you about the vehicle, what it is. So in this case here, we can see the type of a cabin heater it says heat pump there. So I use my little arrow here to show you that it says heat pump. If it doesn't have a heat pump, it will say resistive heating. So, and that's with our PTC heater, which is an electric heater that draws directly from the high voltage battery to heat the cabin of the vehicle. So as we move on here, one thing about heat pumps is because they're so efficient, and we can always hear about efficiency, whether it's a heat pump on your house or in a vehicle. We hear about the increased range with heat pumps and so on. One thing that we do see, though, is that because heat pumps are so efficient, their numbers exceed the efficiency percentage. So we have to, they created a new term called coefficient of performance. And that means what you put in, you get more out of. Currently, PTC heaters and resistive heating systems are 100% efficient, effectively. So how can we get a system to be more efficient than 100%? And that's why they came up with the COP. And this means that the energy I put in to how much I get back out. For example, like a resistive heater can draw up to about 7 kilowatts of energy. And that will heat up the cabin of the vehicle up to about 27 degrees Celsius, and so it's pretty good. So we're looking at about 85, 90 degrees Fahrenheit. If I can take and heat the cabin up to that same temperature, only using 2 to 3 kilowatts of energy, I've gone beyond. I'm more efficient, even though I know the PTC is 100% efficient at 7 kilowatts, at 2 and 3 kilowatts, and I can get the same performance with the lower amount of energy, makes me even more efficient. In fact, they claim that the Tesla in equivalency to efficiency would be about 300 to 400% efficient. So, but it's a number that we can't really relate to. So they use this definition of Q and W, basically the quality of the work heat transferred to the amount of work put into it. So that's our energy going into it, and of course what we get out of it. Oops, down here. So coefficient of performance is a term that you might have to start talking about, especially with heat pumps. And if you're doing, and also just to back up a little bit, heat pumps aren't new. They're fairly, they've been around for a while in cars, especially with the Nissan Leaf in about 2014, maybe a little earlier than that. We've seen in the Konas and so on. Some of the other models had heat pumps for for a variety of different systems, especially on electric and hybrid vehicles. But the coefficient of performance heating mode, basically how efficient a heat pump extracts the heat from the source and delivers that heat to a space, as well as the cooling mode. COP can be also measured on the cooling side to measure the efficiency when the heat pump removes heat from the conditioned space. So just like air conditioning, we talk about the heat removal, heat movement, and so on. But the COP of 4 means that every unit of energy input work that puts into a heat pump delivers units of heat energy. So right now, that's where Tesla sits at, about 3.5 to 4. You might correct me on that. I've heard different numbers, but in around that range. So whereas 100% efficient is 1, COP of 1. So Tesla's pulling out 3.5 to 4 COP, which is pretty impressive. So one thing about heat pumps that is not ignored is the basic fundamentals of refrigeration. I'm not going to go through, what happens what's inside the refrigerant cycle and so on, but you must have an understanding of the refrigeration cycle. In this example, the refrigeration cycle in this TXV system is a very simple system. It functions, by removing heat and getting rid of heat by convection. So the thing is with the heat pump system in Tesla, they actually have 6 TXV valves, and they do different things within the Supermanifold. So, but one thing I just want to put the fundamentals down there is that one thing we have to make sure is that we understand that heat moves from hot to cold. That is a basic foundation of this Tesla heat pump system. Everything contains heat, everything. Ambient air contains heat. Any the products that we touch and things that we feel contains heat. Change of state, when we have the change of states, whether it's evaporation, condensation, or freezing, is absorbing or giving off BTUs. Water boils because of impurities, and that's super important. We talk about, when we talk about water boiling, we see that there's impurities in water which cause the water to boil. Water evaporation is not the process of boiling, but is reaching an amount of BTUs within the water to cause the evaporation, to cause it to change state. Super important within heat pumps, and you'll see why in a little bit. Superheat is adding more heat after the vapor above its boiling point. So once again, superheat happens, within the compressor. We always talk about that, and I'm using that as a perfect example of what's going to happen in the heat pump system here. Subcooling is cooling refrigerant further beyond saturation temperature, ensuring it stays as a liquid as it enters into the system before the expansion valves and so on. We don't want any vapor in that trapped in there, which could skew the performance of the heat exchanger at that point. As well as heat moves in three different ways: radiating heat, sensor radiators; conduction, touching, moving heat through conduction, and transfer, as well as convection and moving the heat from one area to another. So these are some of the basic principles of refrigeration. Super important with heat pumps. First generation of Tesla's cooling pass. I'm just going to go through this quickly. This way you'll get an idea what's happened with the Octovalve. The Octovalve is basically a valve that moves coolant in different areas based on demands or requirements, whether it's a passenger or the system itself. So first generation of cooling pass, non-heat pump. I have a kind of a shady little PowerPoint here to explain it, but just give an example. This is the electronics. So in the very bottom right corner, you see that little orange hex box there? That is representing the not the Octovalve, but the four-way valve. In fact, it's actually 5 valves on it, but 4 are only for passages, 1 is a blocker. And in this case here, if I want to cool the electronics of the system, the MG in the back of the vehicle or in the front of the vehicle, depending if it's an all-wheel drive or rear-wheel drive, contains heat, has heat within the stator. The stator basically gives off heat, oil is pumped over the stator, and that oil is moved to a heat exchanger in the back, which is represented by HEX there. So we see the heat leaving with coolant and the coolant going towards the radiator. Now, as it goes towards the radiator, it's going to go down towards a blocker there. So it's been blocked, so it can't go through the battery and so on in this demonstration. So that forces the coolant through the radiator and now into the four-way valve here. So that four-way valve will take that coolant, move it through that after it's been cooled, move it back down towards the electronics, back towards the motor itself, and it keeps doing that path. I'm just showing this as a one step in the simplicity of the cooling system. Example on a 2018 to 2020 Tesla Model 3 would be an example of this one. Now, if I'm doing the battery, when I'm cooling the battery on the system, so the same thing kind of happens. The battery system has its own pump. So you see their DSP and our PSP. That stands for driver side pump and passenger side pump. So in the previous photo I had there was 2 pumps on the front of the system. And I'm just going to go back up here again. I'll show you real quick. The 2 pumps I'm talking about are right here on the passenger side. And then there's a driver side pump. We have a chiller here. We have the air conditioning compressor, and of course we have our refrigeration lines, and of course a condenser in the front and coolant lines as well. So as I go down into my battery, I can see that first thing that happens is that the air conditioning compressor turns on. Essentially, anytime there's heat, especially in a heat pump system, that compressor is going to be running. So in this case here, the AC turns on, which is basically feeding refrigerant to an expansion device into a chiller, which is acting like a little mini evaporator. And what happens as the hot coolant leaves the high voltage battery, it travels down through the four-way valve here. It moves through that valve. The pump is pushing it or pulling it and pushing it, goes through the chiller where it's cooled, and then it goes back into the battery. And this loop continuously happens. One thing you notice is that essentially the radiator is not involved with this process. The chiller actually works as a heat exchanger, removing the heat from that coolant and basically dissipating it back into the refrigerant, where the refrigerant carries it back to the compressor, sends it to the condenser in the front of the vehicle. Now, the part I really love about how Tesla does their heating. How do they heat the battery? You got to understand, Tesla, especially in the Model 3, Model Ys, and so on, They don't have battery heaters like other manufacturers may have. They may have a physical battery heater in there, or they may heat the coolant with their own PTC in some way to warm up the battery, especially on preconditioning or even on when a battery is cold to get it back down into a temperature range. Well, in the Tesla, where they get that heat from is the electronics, from the battery, and or sorry, from the motor, the drive unit, and so on. So in this case here, the MG is actually energized. In the case of the vehicle stationary, or even while driving, it can make it very inefficient, the motor, and the stator gets really hot. And that oil is pumped over the stator, getting hot, knows the battery is cold, so it needs additional heat to help heat that battery up. So what happens is the battery is, or sorry, the motor is fielded, it gets hot, the stator picks up the heat to the oil. The oil is then transferred to a heat exchanger on the drive unit, and then that heat is transferred into the coolant. And then that coolant will actually be pushed back through the battery. So if you see what happens here, we turn the AC. So on the cooling cycle, the AC is off. Okay, we want to heat the battery, but watch what happens with the valve now. The valve actually turns. So this valve turns to change the direction of flow within the cooling system. So now the heat leaves with the heated coolant, goes through, and at this point now it doesn't go through the radiator because the bypass is there. The bypass is now open. Coolant can go through the valve itself. And then on the other side of the radiator, any coolant that does get pushed down through the radiator is blocked anyways at the bottom of that valve. It doesn't go anywhere. And then, of course, now the pump takes that hot coolant, puts it through, the chiller is turned off, there's no refrigerant going through, and goes into the high voltage battery. The battery picks up that heat, and basically the coolant picks up the heat and continuously travels it back down through. It goes down, it's cooler because it's dissipated that heat into the cold batteries, and then it moves back into the motor where it picks up the heat again and moves it around. So this is the first generation of how they would control thermal management within the battery and within the electronics of the vehicle. And obviously, with this car, it doesn't have a heater core. It has what we call a PTC heater. And in the PTC heater, there's a driver's side and passenger side. It was high voltage directly from the battery, draws a lot of energy. So this system worked well for the battery management and electronics, but it also drew a lot of energy from the high voltage battery. So that's why we went to the Tesla heat pump system. So the heat pump is way more efficient. It turns a compressor. Yes, it might run almost all the time, anytime there's any kind of heat movement. But this system is very compact. It does many different things. It has 30 different operational modes, I guess you could say, as well as it's a 4-valve manifold system. So the Octovalve, hence its name, the Octo, for being like the octopus, which we're going to see in a little bit, is essentially 2 of these valves in this left corner here. Gotta make it turn here. So this little guy here are 2 of these built into one valve itself. So, and I'm going to go into that a little bit here in a second. But you can see here we have one. I actually have this unit here for teardown. Hopefully we'll be able to get to it. I'm going to go through this fairly quickly, high level, but give you an idea of what these components are, what they do, and how they work. Okay, so I'm going to move on here. Tesla's heat pump system is a combination of refrigerant, coolant in one module. So that's a cool thing about it, no pun intended, but we have the cooling system and we have the refrigeration system in one package. And that's the beauty of this system. That's why they can integrate it into other vehicles. There are 2 valves that control coolant flow. So basically the Octovalve. So it's 2 valves on top of each other, really operating all different types of pathways for the coolant to flow. The kicker is there is no condenser on these vehicles, not conventional condensers. So as we're used to even seeing the Tesla Model 3 in the 18, 1920s, or even earlier in the S's and X's, we see these condensers in the front with the radiators. There is no condenser on these vehicles, not conventional type of condenser, nothing in the front, just a radiator. Larger radiator than previous models. So it's actually, when you look at in the front, you're going to notice it looks like the same size as the condenser, but it's not. It's actually the radiator compared to non-heat pump vehicle. There's several expansion valves. They're very unique. They do lots of different things, and I'll explain that as we get into it. But there's 6 in total on this Supermanifold. Condenser and evaporator are built into the same case. I did mention there is no conventional condenser, but there is a condenser on this vehicle. It's actually inside the air box inside the vehicle, alongside the evaporator, and they're both exposed to each other, and they have unique principles in how they operate based on that. Liquid cooled condenser. So when I mentioned we don't have a conventional condenser, we do have a condenser on the Supermanifold. It's called an LCC, liquid cooled condenser. That means that the plates of the refrigerant, the hot refrigerant, actually come in contact with the plates of coolant running inside that unit. And I'll show that in a few minutes here. Massive strategies. The biggest thing with this Octovalve system with the Supermanifold is the strategies that are incorporated into it and how Tesla is reusing components already on the vehicle to achieve heat, and cooling effects within that vehicle. A lot of modes are dedicated to getting heat to help cool the cabin, heat the cabin, heat the coolant, heat the battery. All these different modes play within the system. All Tesla heat pumps are the same, so I just mentioned that, except one removable coolant container. So the only difference between the Tesla Supermanifold and Octovalve from an S and an X to a 3 and Y is the coolant reservoir bottle. That's the only difference. So if somebody had a Tesla Model Y, Supermanifold, and they wanted to put it in Model X, it would be interchangeable, except for the coolant bottle would have to be replaced. It's compact all-in-one housing, reducing well over 20 different parts compared to other models of vehicles that use heat pumps. When you open up some of the vehicles like the Leaf and stuff like that, it looks like basically a refinery of piping and plumbing and valves and switches and so on. Tesla has incorporated it all into one. Here, get down. My mouse keeps moving. Here we go. Heat pump systems must do this, and this is the strategy that they have to do. They have to heat or cool the cabin, they have to heat or cool the battery, they have to defog the windows, has to have that capability, they must work in sub-zero temperatures, and operate as close to the performance of heating as a PTC heater. And that's kicker, because as we know, whether it's a heater core in a vehicle or even a condenser in front of a vehicle, obviously the condenser has now been placed into the heater box. It takes a few minutes for that heat to be transferred into those components. Tesla has done something very unique to these vehicles in helping with that heat transfer. Here we see on the right side, I was putting this up here because part of what we do at ConsuLab is find innovative solutions for teaching multiple different types of technologies. So right now, you're probably some of the first people to actually see this. I don't know if I get in trouble for this, but this is actually one of the prototypes that we're building right now for ConsuLab is a full heat pump system with high voltage battery heating and cooling, with a chiller, refrigerant cooling system, all in one unit. But what we did uniquely is that we made it so it represents all vehicle manufacturers. We even still have the heater core inside this unit and so on, but the principles don't change. So what we learned in the Tesla heat pump system is definitely applicable to what our trainer does, as well as our trainer is applicable to the heat pump systems in all different types of manufactured vehicles, which is really cool. We're excited to see this come out within the next little bit here. So this is Tesla's heat pump layout, and this is all models. So what we can see very quickly is we can see that inside the air box here, we have an evaporator and condenser. We have our switches here, and we have a coolant side. So really, These guys here from the LCC, which is our liquid cooled condenser, and our chiller basically separate the system. Inside the air box is the evaporator, and then we have the condenser. They're both inside, and it's just a regular type of condenser. Obviously, it's not huge, it's small, it's very efficient, as well as the evaporator. And the fan actually blows over the evaporator first, and then pushes over through the condenser, which is very interesting, what you're going to see in a few minutes here. We have a high voltage AC compressor, and we also have an accumulator, and we have a chiller over here as well. And then there's our valve system we talk about in the Octovalve, and that's our Octovalve here itself. One of the things I'm going to talk about real quick here is some of the cool things that the Tesla does. In fact, if I look up here, it says I have a low voltage heater. And I've taken these cars apart. I've stripped them down, I've pulled them apart, cutaways, and so on. And I've never found a low voltage heater inside a Tesla Model 3 or Y or X. And I was like, where the heck? Like, and I went to the patents in Tesla and they didn't have any. And I was like, where are they getting that low voltage heater from? And actually, they get it from here. The three-phase DC brushless blower motor. They already have a built-in PTC heater essentially within the airbox itself. This blower fan is very unique. It's a three-phase brushless DC motor, and it's basically generates heat. As the stator is operating the fan, it gets warm. And if you look at the design, and it depends on how clear you'll see how the blower fan is actually underneath. You can just see the shadowing there of it. And also look at the edges here of this fan. It goes beyond the squirrel cage here. It's to catch the heat leaving the stator. It grabs that heat and pushes it through inside the vehicle. So on a cold morning, you turn your fan on because you're going to be defrosting your windows and you got it. And instantly, as that stator starts to get hot almost instantly, it can actually provide a little bit of heat. It's not going to heat the cabin up itself, but it will give those customers that used to own, let's say, a 2019 Tesla Model 3, now they own a 2023, they get in their car with a PTC heater, it's instant heat. Now they get into a heat pump vehicle and they feel the warm air coming through the vents the minute the fan is on. Very unique, but it also serves another purpose as well. So we'll see a little bit here in a second. The high voltage air conditioning compressor as well as it's a three-phase motor as well too. The inverter is actually built into this compressor, and it serves also another purpose. Because we now know, because of a stator getting hot, it can also, help heat refrigerant. So if we want to increase the superheat of refrigerant as it enters into the compressor, they can actually make the stator even hotter by creating an inefficiency within the inverter to the stator. So, making it really hot, squirrel-style compressors. So the compressor is actually a source of heat to help with heating the refrigerant to make it more more efficient, I guess you could say, at dissipating the heat, especially when it goes into the cabin. Because understand the refrigerant flow from the compressor, it goes out to my receiver dryer, and then it goes into my condenser. And guess where the condenser is? The condenser is actually inside the airbox of this vehicle. So the more the BTUs it can gather within the compressor and absorb into that refrigerant, it can be sent to the compressor, sent to the condenser, making the condenser hot, which will give the heat to the inside the cabin. Where else they get the heat from these units is from the drive units themselves, the electronics within the vehicles. They can gather heat. The stator itself, I mentioned at the beginning, same thing on a heat pump vehicle. And this is another thing that makes the vehicles more efficient when you drive down the road, is that as you go down the road, the vehicle itself, the stator, can become inefficient by changing the offset of the phasing. Typical phasing is 120 degrees. If I move that phasing away, that stator becomes very inefficient. It gets very hot. They start pumping oil over those coils and basically picking that heat up and sending it to the battery. So if you're driving in a car and it doesn't have a heat pump in it. It's a Tesla. As you're driving down, you see preconditioning happening on your battery. Essentially, that's what it's doing. It's using more energy to do it to get ready for supercharging or fast charging of that vehicle. At the very bottom picture here, we see the heat exchanger that's attached on the top of the drive unit. And this is where the oil is put into this little heat exchanger and coolant is pushed through it. And that's where it picks up that extra heat to help heat the battery and so on. So it's, once again, very unique way that Tesla does these things. The Octovalve is a 4-position stepper motor, 4 configurations of coolant flow. There's 8 valve openings. It is serviceable. That means you can replace it. And the motor is on the bottom with the position sensor. So it moves in 4 different positions. These 4 different positions allow coolant to do different things. I'm not going to go through all these because of time, but this is from a different course. But, we can do all the different requirements for the vehicle system itself. These are some of the configurations that these valves do. So as it moves in these 4 positions, it moves coolant into different areas. And then, of course, the chillers will remove heat, or, in the sense of an LCC, that's a liquid cooling condenser, which is part of the Octovalve system. It can actually move heat there. So very, really cool system itself. The Supermanifold, which is the other side of the system, basically is incorporating all these plumbing and everything that you would see in a traditional heat pump system into one unit. So we see that we have lots of expansion valves here. So we have our recirculation valve that usually doesn't open up until it's really, really cold. We have our LCC, that's our liquid cooling condenser. We have a shutoff valve here, that's a solenoid as well. We have for basically our right and left side of our condenser inside the vehicle. We also have our chiller, and we also have our evaporator as well too. So these are thermal expansion valves. And one thing about these is these guys on the bottom of this diagram are probably all on the low side of the system, and these are all on the high side of the system. And then, of course, we have our 2 compressor from compressor. We have our sensors for temperature and pressure that protect the system. But if there is one thing I didn't mention here, this is actually a fail-safe device. So if these solenoids are actually either on or off, or they can be pulse width modulated. So if they all failed and stuck shut and the compressor is compressing, the pressure would go extremely high. This SOV, basically for the LCC, opens up and it relieves the pressure from the system. So it doesn't allow the system to become damaged or whatnot, causing failure within that. So I'm at the point here. I'm just going to see if anybody has any questions real quick. Anybody have any questions?
So far, there are no questions in the Q&A, but I highly encourage everybody, put your question. I don't know if they're enthralled, you've blown their mind, or they're I don't know.
I just want to show real quick here. Here's a Supermanifold. It runs a couple minutes. So this is a Supermanifold here. And just to show you real quick, I have my camera on it. I'm going to take out, I only put a couple screws in these things because that's how you put cars back together. We're smarter than engineers, so less parts and it still works. That's the thing. So right here, this is the coolant bottle I was talking about. So if it's a Y or a S or X, that's what you replace. So everything else here is standard. I can move this off to the side here. I'm going to take off the Octovalve first here. Doesn't really matter. Usually I don't put. So this is the Octovalve set up here. And you say this is a replaceable part. In fact, on the top here, as I'm doing this, you can actually see there's a picture of an octopus. And this valve here itself is kind of cool because it basically takes that first generation of valving, those 4 valve positions, and they've just doubled them up inside here. And this is where all the coolant passes through to make its changes here. So you see this here. We have the 8 different ports here on this Octovalve. And basically, depending on the position where it's going to, more coolant, more volume through there. These ones are individual passages for different placements on that. As we can see on the bottom here, there's the motor that turns, and also there's a position sensor inside this connector here, which then tells position of the motor, and it turns like this. It can actually go like this, or it can go like this and go around like that. So, and inside there's the vanes for the passages where that coolant is going to go.
Dave, we have a question.
Sure.
What is controlling the Octovalve? What module?
It would be the I'm going to say it'd be the high voltage, not the high voltage, it'd be the HVAC module for the vehicle. So it'd be incorporated within the MCU. So the MCU in like the Model 3, Model Y would be in control of this this module itself. In the accident, I'm not 100% sure. I'm sure it's all through the MCU because all the climate control and everything is controlled by the MCU, as well as when you're in the MCU, you also see the type of system that's there, as well as the operation of the system itself. So don't quote me on that, but I'm pretty confident it's the MCU that's in charge of this this system. So that's the main control unit for the vehicle. So what I'm going to do is I'm going to pull off this manifold here. So you can see I just got 1 bolt in this guy here. And we got our 2 pumps. So pumps do individual things. So we have my powertrain pump and we have my battery pump. So obviously they have their ports as well here for plugging in. And then on the back, this is all one piece, by the way, too. So it's like a blown molded plastic, you know, been done for years. And then I have my coolant passages for the LCC, as well as my chiller passages here. And then, of course, my, you know, once again, my powertrain return here. I got going out to the radiator in the front of the vehicle and then from the radiator. So this guy's like the big control device for the vehicle. And I'd love to go through more with it. I know our time is really short.
And we do have another question as well.
Sure.
Is this low voltage controlled?
Yes, it is. It's low voltage, up to 16 volts. So whether it's a low voltage system or you know, on the newer ones with the lithium low voltage battery, yeah, it's all low voltage controlled. In fact, even these little electric motors, everything is all part of the low voltage system. No high voltage in this at all.
You know how everybody still is a little uncertain about the voltage and getting themselves hurt or killed dealing with these EVs, so it's probably a normal question to ask.
Yeah, low voltage is a very an interesting term because we can go anywhere from what operating voltage of 13 point, well, if you want to go to even lower, 12.6 all the way up to 48 volts. So it's you know, once again, I'm sure on the Cybertruck, I don't know on the Cybertruck if they're using this exact same setup. They probably are. But the thing is that it's got what do you call it? It's got a 48 volt system on it. So I'm sure the pumps in that and sensors are all typical of that system. So this is basically my LCC. Really nothing super special about it. Refrigerant in, refrigerant out. I got coolant in, coolant out. But one thing is unique. I don't know if you can see this, but in between each one of these plates, you'll see there's like a plate, a plate, a plate, a plate. Then there's another series of plates. And what they do is they actually interact with each other. So as the refrigerant cooling are going through, this is acting like the condenser. So this is my LCC. So this is our liquid cooled condenser. It's fairly large compared to my chiller down here. And as I go down into my chiller, got only one screw in this one, not as long, thank goodness. And here's my chiller, which is very similar in the sense of how it looks inside, you know, but basically it's a lot smaller. And essentially this is, you know, really getting rid of heat. And this is, you know, once again, trying to put heat back in or get rid of heat within the system itself. So we have a chiller and then we have our condenser. So they both actually work opposite of each other when you think about the heat exchange that happens with them. Within the Supermanifold, One thing I did mention at the very beginning, I talked about the serviceability, about the purity. One thing about electric vehicles, they rely heavily on their thermal systems, air conditioning systems, especially ones that are thermally managing the batteries by either putting heat in or removing heat. And within these guys here, it's super critical that these desiccants are replaced. And you guys are going to laugh because they don't come apart that easy. So I'm going to get a little bit of, I still have a little bit of oil inside this one. I have another unit that I have a cutaway, but it didn't get completely finished. So this one's another just a unit that I had. But you see this desiccant, it's replaced. It's easy to get at. Whether it's the earlier Teslas or later Teslas, this desiccant needs to be replaced. And there's actually a passage that goes in here. So it's fairly easy service. You drain down the refrigerant. You basically unscrew the top. You pull the plug out. It's actually a plug that looks like this. And then it lifts off. And I find that sometimes you'll see it's a little thread here. So actually a net will fit on it and you put something underneath and pop it up. They aren't the easiest things to get out in some cases. More importantly, is what go through here, and this will be probably where we'll end it. We have these solenoids on here. These are solenoids that control different passageways within the unit itself. So if I flip this over, I put in here just basically where these solenoids are dots, that's where they would be located, and shows how the refrigerant flows through that system. So we have check valves here. So this is a cabin check valve. So this prevents refrigerant from going backwards in the system. We have a check valve here for the LCC. I had to think for a second which that one was for. So there's 3 check valves on here. We have one for the liquid cool condenser. We have another one down here for the evaporator inside the cabin of the vehicle. And of course, on the other side, we have that other check valve. This is my shutoff solenoid here. This is a safety system. It will open if these solenoids all close with the compressor running. We have our temperature pressure switches, whether they're low pressure vapor, or sorry, high pressure vapor, high pressure liquid, and of course low pressure vapor in the system. There are also temperature sensors, and these are just simple solenoids, 4-wire solenoids. They turn on and off, and these are, so either they're on or they're off, or they can be variable. So they have that option to be able to do that for refrigerant flow in the system. The kicker is these are not serviceable. So, and this is what happened in the early Teslas. They had some software issues that they were causing these not to give any kind of heat inside the vehicle. We had a lot of these actually when we were down here in Halifax. So, and this was probably one of those units that came in, or what happens, one of these valves fails inside. And when that happens, and of course, then you don't have any kind of thermal exchange within the system, not properly or effectively. Last thing is I'm going to show, this is my last point. One thing you're going to notice, I got some oil leaking out here, so I'm on a different table. You're going to see, maybe I'll do it on the other side, might be easier. Oh, flip this over. You'll see, sometimes some people say, look at that, there's a crack. Look at all these cracks in this housing here. So they all go through all these different areas. And because the type of this material, it's a very soft material. Sandy Moreau had a really good explanation of the build of these. They actually put these cracks in here. They cut it that way so they can expand and contract. So otherwise, they would cause these to fail probably prematurely. So they actually put these cuts in there to actually do that. So anyways, that's it for the high overview look of our thermal management systems, and specifically the heat pump system of a Tesla Model 3 and Y and X and S. And that's kind of where we're at.
Well, Dave, I don't see any more questions in this, so I guess we'll wrap it up. I want to remind everybody you will get a certificate of participation for your time here. We appreciate that. We also want to wish everybody a restful and peaceful holiday break coming up soon. I know we all could use that. Also, I'd like to remind everybody that our next webinar will be January 15th, and we're going back to the basics. So if this was a little over your head, January 15th, we're talking basics of electrical troubleshooting. So we're trying to cover all areas that you may encounter with you and or your students. And as always, we want to be your partners for all things automotive. And we appreciate your time. We thank Dave as well for his time. And be sure to continue to follow us on social media and our YouTube channel, which is ConsuLab or youtube.com/ConsuLab.
Great. Well, thank you guys very much and hope you enjoyed this. And yeah, look forward to our future webinars. They're just going to keep getting better.
Thank you,
Have a
everybody.
Merry Christmas.
Merry Christmas to everybody.
Thank you.